All right, I think this should do it. Okay, hopefully the volume is better. I'm not able to increase it more here. Okay. And so yeah, go ahead. Yeah, all the slides and everything will be posted online, and I'll get to where everything is going to be in a little bit. Okay. Yeah. So the recordings will be posted online, the slides will be posted online. What I'm going to write, the transcript is going to be posted online, and you can also track it live. The link is on the website as well. Okay. So we have 5 TAs, 5 excellent TAs. Some of them have TA'd with me in the past, but this course, I know they do a good job with it. And every one of them has their own office hours. So altogether, we have 12 office hours per week. Okay, so there's plenty of time. If you need more, there's always the online platform. So just keep emailing, or just keep posting, and we will respond with hopefully very high in very short duration of time. Okay. And we have discussion sections on Fridays, except for the weeks when we have midterms. And please attend them. The TS will go over solutions to homework and practice problems in there, and previous year's exams and any other questions that you might have. And for grading, the grading is kind of heavy on the exams, right? The homeworks are 24 points for the whole course. We have 6 homeworks, each worth 4 points, typically about 4 problems per homework. And we have 3 exams. The exams are non-cumulative. The first exam is 25, and the third exam is 26. Each exam is 2 hours exactly. And exam 1, 2 will be in class on, well, the dates will come up in a little bit. And exam 3 is as per university schedule. Okay. And I don't like to put strict cutoffs at the very beginning, but I can tell you that it's always going to be towards, to give you an advantage. So typically there are about 30 to 40% A's. I'll move the cutoff only lower and never higher, so that less people or more people get the right grades. Okay. Any questions about grading? Yeah.
Where's exam 3?
The exam 3 is, I think, still to be decided. It should be on the university schedule.
But it's in person.
It's in person. Everything is in person. All exams are in person unless you have an exception that, either granted through, definitely it has to be granted through me, but also has to come through some other things. Okay. Okay, and for homeworks, all 6 homeworks will follow the same pattern, except the first 5 homeworks will follow the same pattern, except the last one. And they'll go live on course page on Mondays at 6 p.m. And they'll be due next Monday at 10 p.m. Okay, and we will use Gradescope for submitting homeworks. Okay, and the homeworks will be discussed, once they're due, they'll be discussed in that week's discussion section. The solutions will be posted online, and the TS will go over them. Yeah.
Is there a reason it's 10 p.m.? I feel like there's like a psychic load that's if it's not at midnight, because you have to keep track of more deadlines, people have a lot of classes.
Yeah, I know, but I realize that, if I do 12 p.m., we keep getting messages at 11:59 p.m. Okay, and by then I'm asleep for sure. Okay, so we want to be attentive to you as much as possible. And also, it's kind of, for your own good, sleep early. Okay, I'm just kidding, but yeah. Okay. Yeah, and homework rules and tips. I say the most important resource for homeworks are the EdSTEM platform, which we'll come to in a little bit. Keep asking questions and use the office hours and start early. Okay, because if you start on Monday morning of the day it's due, you won't have ability to, if you have questions, you can't just come to office hours. Okay, because you'll only have maybe 1 or 2 windows available. And I have my office hours Mondays and Wednesdays, immediately after the class from 2 to 3 p.m. right upstairs in room number 463. And the TA office hours, they're all posted on the course website. Okay. Late submissions is 0 credit, no exceptions. There's no take one out kind of any exception allowed. The reason is that, as you'll see, the attempts count for the homeworks. Okay, if you submit the absolute best solution, you get 100%. But if you make a serious attempt for any problem, you'll get 80% of the credit. Okay, and if you do a reasonable attempt, it's at least 50%. It changes based on the problem. And the most important thing to keep in mind about homeworks is that you should think of them as stepping stones to the exams, which carry a lot more weight, and there's a time limitation on them. So even if you spend a few hours thinking about the homework, I think that kind of trains your mind a long way in preparing for the exam, all right? So make honest attempts for the homeworks, and you'll do well on the exam. And as I said, homeworks are to be submitted on Gradescope. You should, the website is not yet set up, but it'll be done today. And you should receive links to register on it. You can access it, I think, through Bruin Canvas, as well, Bruin Learn as well. So please do that. And another mundane thing for regrades, please submit your regrades within a week of when things were graded. I don't want, like, in week 10, someone saying, okay, in homework 1, I have a question. Okay. So if it's past the first week, we won't look at it unless there's, again, an extreme circumstance. Okay. And please submit the regrade request on Gradescope. This is a big class. We have around 250 students, only 5 TAs. So everyone comes to office hours for regrades. I don't think that's the best use of office hours. Okay. So for regrade request, please use online interaction on Gradescope. If and only if it's still not kind of resolved there, come to the office hours. Office hours, think of it mainly as time to answer questions, okay, about homeworks, exams, and material that you learn in this class. All right. Okay. And collaboration is encouraged. But everyone must write their own solutions. Remember, we are very strict about that. So keep that in mind. All right. And as I said, attempting homeworks honestly, it really has a big impact on how well you'll do on the exams. And it's much easier to keep attempting them regularly than just cramming towards the end of the exam. Okay. And as I said, for the exams, there are 3 exams, non-cumulative. The first exam is on October 26th, which is a Wednesday. It will be here in this class. And it's from 12 to 2. All right. And it covers only the first 8 lectures. Lectures 1, 2, 3, 4, 5, 6, 7, 8. Exam number 2 is on November 16th. Lectures 9 through 14. Exam number 3 is December 6th. That's the university schedule. Okay. It was meant for 8 to 11, but we'll only have it for the first 2 hours. Actually, I should say it's 1 or 50 minutes. That's the usual class deadline. And it covers the remaining 6 lectures. All right. And as we get closer to the exam, we'll have last year's exams available for you to practice, and the solutions also there. Yeah.
Will the lecture and discussion be recorded?
The discussions, I don't think so. The lecture will definitely be recorded, and they will be available online. Hopefully, I'll improve the quality because it's just now being recorded on the MacBook Pro, but hopefully they'll definitely be recorded and available. Discussion sections, I don't think so, depending on the facilities in the rooms that the TS are going to be in. Yeah.
So can we go to whatever the discussion, or should we go to the one that we?
I strongly recommend going to the one that you're assigned, because otherwise things might become, kind of skewed. Again, as I said, it's a big class. We have 5 TAs. If all 100 show up at 1 TA, it's going to be hard. Okay. Is there a question somewhere there? Any other questions about the exams or homeworks? Okay. And one of the main resource or main sort of launching point for anything that we do in this class, for any links, will be the course website, which is this one. And so whatever I write, all the slides and everything will be available there and on the EdSTEM platform. Most of you, whoever was registered at least by last week, we took your emails from Bruin Learn and sent you an invitation through EdSTEM to register for this class. But if you haven't, please go to the course website. There is a link to register and do so, because all announcements are going to be posted there from now on. SM is basically just like Piazza, but I just like it slightly better because it allows me to have videos embedded in the in the website and so on. Okay. So if you go there, there'll be a lessons tab where, right now the lectures to come in the future are, you can't see them, but, as we go along, all of these lectures will be visible to you. All right. And once you click on a single one, it will have like, lecture video, lecture notes, and, if there's some code to go along with it or any other external links, they will also be available. Okay. I'll post the videos on YouTube and kind of embed them in the website. Okay. Any questions about it? Okay. And so in terms of resources, the main textbook we will use for this class is Introduction to Theoretical Computer Science by Boaz Barak. It's a free online version, online text. If you go to this website, intro-to-tcs.org, you can access it. And so the text is kind of a new take on the same topic. So our version of this course is different from the other versions, even within our department. And this is kind of a redesign of the course. We're going to cover some topics which are not present in other equivalent versions. But I think, it's these are good topics to cover. Okay. And please keep asking questions, especially, why we are doing something or why we are covering something, why we are not covering something, or if anything is not clear. And yeah, go ahead.
And they have a chapters for each lecture. Do you recommend reading those lectures or actually just watch them?
If you attend the lecture, that's fine. And in terms of reading, I think it helps. The book is much more detailed. As good as the book is, sometimes it is way more detailed than what we would want to, because, we are a 10-week course, so we are kind of covering some parts of the text. Okay, so the book chapters are meant like, mainly if you want to dig deeper or you want to get a revision, then go into them. Okay. And in terms of asking questions, office hours, again, as I said, they happen only, at least each person's office hours happen only twice a week. So they're high latency. But at the same time, the advantage is that many of you show up and then one person's question kind of answers many other people's questions. Okay, and sometimes something you might think something is clear, but then another student asks a question, then it becomes even more clear. Okay. On the other hand, EdSTEM is low latency because, as soon as you respond, as soon as you post a question, hopefully one of you will answer it, or, one of us will answer it. Okay, let's think of it as a race. Whoever is going to answer it first. All right. And I'll create separate threads for each problem in the homework so that all the questions about the problems and so on are kind of focused and easy to look up. And throughout the course, and I'll send out 2 surveys to kind of, help make the course better. We're kind of, as I said, the topics are somewhat new and the format is again changing a little bit. This hybrid format is maybe only the second time I'm doing it. So we'll see how it goes. All right. Just to summarize, the main tools are the course website, which has links to everything. EdSTEM for lecture notes, lecture videos, questions, discussions, homework exam solutions, and Gradescope for submitting the homeworks. Okay. Any questions about these things? I know it's kind of messy to have 3 different, things to look up, but that's the best fit I have right now. Maybe one day BruinLearn will become the go-to, but right now this is better from what I have in mind. Yeah.
So we're not using BruinLearn at all.
No. Yeah. Any other questions?
Will exams be posted on Gradescope? Exam grades?
The exam grades will be on Gradescope. Yeah, I mean, this course will be on Gradescope. Everything will be on Gradescope, and at the end, I'll just port them back to BruinLearn. Any other questions? Okay. And all right. So now let's get to the more interesting stuff, which is actually what this course is about, right? So the course is kind of trying to quantify what we can compute, what it means to compute, and what and why of computation. All right. Okay. And let me just go to the course website. So this is what the Edstone platform looks like. If you go there, you'll see these things. Later on, we'll also have some code demos. You can see discussion. Okay. And where is the course? Because this is a course website, and one confusing thing that I had people people kind of put them off is that these little triangles are actually clickable bullets. So if you don't find something, just click on them and you'll see it. All right, so all the details are here. And maybe the thing that you might need the most is the Zoom link and the course notes here, which if you click, it'll take you to whatever I'm going to write. Okay. Which is here. Okay. Any questions? All right. If not, let's get started with the actual course. You know, we got rid of all of the logistics and mundane stuff. Now for the fun stuff. Okay. So what this course is about is a kind of, as I said, you know, it's about trying to formulate what it means to compute something and what you can compute. Again, we are impervious to time. We want to build a theory which can stand the test of time in the strongest possible terms, right? And to kind of give you a sense of the challenges or differing views that might be there around this topic, here are some quotes. So Edgar Dijkstra, you might have heard of his name, you know, Dijkstra's shortest path algorithm and so on. He's one of the founding persons in algorithms and distributed computing in particular. And he said, computer science is no more about computers than astronomy is about telescopes. Okay, it's either from a very theoretical standpoint, like computer science should be about what we can compute, irrespective of the exact hardware thing that you're using. At the same time, you know, someone from a hacking background said, you know, hackers need to understand the theory of computation about as much as painters need to understand paint chemistry. Okay, which I disagree with. Hopefully, you know, you will disagree with too as we go along. All right. And finally, here's something that is a very basic question and is something that we're going to talk about again and again in this course. Maybe not in this level of detail, but something that we're going to aspire to. So this person, Aleph Cobham in 1964, was asking, what's the best way to, is it harder to multiply two numbers than to add? Everyone has a sense that multiplication is harder than addition, right? It takes more time, you know, you have to write down some things, you know, if you ask a grade school student, then definitely multiplication is harder than addition. But can you actually show that it is indeed harder? In what sense is it harder? Maybe one day I'll build a special purpose computer for which multiplication is actually easier than addition. Is that possible? Okay. So those are the kinds of questions that we are kind of hoping to answer, or at least build a theory which will allow us to answer. All right. And today's class, let me make sure I see if there are any online questions. Yeah, okay. So today's goals are, you know, we talked about the logistics, and just to kind of give a hint of what we're going to do, we start with something even simpler, which is kind of two aspects of computing, and then we'll start digging into that. Okay. So whenever you think of computing, there are two aspects. I mean, again, this is all made up, so it's not like, you know, my two aspects will be the same as your two aspects, but I have two specific things in mind, right? If you think of a computational task, there are two ingredients which are important. The first is, you know, any guesses what might be the ingredients? Yeah. Yeah. Again, you know, there's no computer here. We're going to build a theory, right? So I'd say, the first thing is you're going to compute on something. Right? So there's some notion of data that your computer has or is using and then trying to do something with it, right? So, and then algorithms, which are just operations on data. Okay. And data is just like, another word for representations of objects. Maybe you're computing on an image, you take an image, you're transforming it to something else, you're taking a text, translating it into another language. Maybe you're taking a graph, trying to find who's connected to who in this graph and so on, right? So all of these are different kind of styles of data. Each of them represents a different object, okay? And every one of them, in every one of those, we are doing a different algorithmic operation on them. Like, we're modifying it maybe in some way, or we're trying to figure out something about the data, okay? So today and tomorrow, we are first going to talk about representations of objects, right? We're going to talk about how to compute on things soon. But first, we need to understand how are things represented on any of these devices that we have, right? At the end of the day, this hard drive doesn't have an image in it. It doesn't have, a text file on it, right? If you go completely underneath, it's just a sequence of zeros and ones. So how do we go from there to what we see up here? Okay. It seems like very, very daunting, right? There's so many levels of abstraction, but what saves us is, as we'll see, composition. Okay. Okay, but let's not jump ahead. Let's talk about what it means for representations. And one thing to keep in mind is that different representations of the same object can have dramatic effect in computation. Okay, so let's take an example. So there is Roman numerals. Okay, you can say, what number does this represent? 42. Okay, does anyone know 42? Why 42 is important? Yes. Okay. And there's also, that's one way to represent numbers, right? Both of these are very old, but this is not the one that we use today. What we use is called the place value system. It's actually very old. It's like almost 4,000 years old. And it's due to Babylonians. Okay, so they introduced this system to represent numbers, which is, for us, just a form of data. So if I were to write it, it just seems 42, okay? No big deal, we have just two different ways of writing the same object, which is the number 42, okay? Doesn't seem like a big deal right now, but suppose I ask you to write the distance to moon. Distance to moon is something like 259956. I have it written up here. And that's how many miles, I think. But if I ask you to write it in Roman numerals, what would happen? I think you'll end up filling a full book. Okay, so just imagine, right? Take yourself back to 2000 years ago. If you are using Roman numerals, if you can't even write the number which represents the distance to moon, would you ask the question, can I compute the distance to moon? Okay, I mean, you might maybe, but then on the other hand, if you're using place value system, it's much more succinct, right? So the two representations of the same object have such a huge difference in efficiency. And as a result, in also on what you can compute on top of it, right? And this is something that will show up later on as well. So representations of objects are what we really call data. Okay. So that's an example of the power of efficient representations. Like in an inefficient versus an efficient version, there's a dramatic difference here. And the same thing happens when you think of algorithms, or operations. All right, again, let me give a simple but kind of extreme and illustrative example. And one of the, first, I say non-trivial algorithms that many of you see is multiplication, right? And let's say there are two simple algorithms for doing multiplication. What's the first one? So what do you mean by multiplication? You're given as input two numbers, X and Y, and your goal is to output X times Y. Okay. So what is one sort of simple or the simplest algorithm for multiplication? Any guesses? Like if I ask, yeah, go ahead. Repeated addition, right? That's what my 5-year-old would probably do. Okay, so you start with result equals 0. Okay, and then I keep going for I equals 1 through X. Result equals okay, and then you return the answer. Right, so repeated addition just means I'm adding Y to itself X number of times, and that will give me X times Y. Okay, that's one algorithm. There's another algorithm, which again is probably the first real algorithm that any one of you has seen, probably without realizing it, is grade school multiplication. Right? So I give you as input a number X, maybe it has n digits. Let me write them in reverse order. Okay. And how do you go ahead? You say, okay, let me start with result is 0. And you write down a for loop. I mean, you probably weren't writing for loops when you're in grade 5, but you are kind of implicitly doing that. Okay. You just set result to plus. Okay. This is just fancy notation for, when you write down, the multiply one row at a time, kind of keep shifting and then add them up in the end. Okay. This is the exact same thing. There's nothing different happening here. All right. But let's compare the two algorithms, right? Which do you think is a better algorithm? The top one? Okay, let's see why and compare them and see. And better in what sense? So let's compare, right? So if we raise them against each other, what happens? Suppose you had two 20-digit numbers. that you had to multiply. Right, for whatever reason, I like torturing fifth graders, so I give them two 20-digit numbers and ask them to multiply. If you use repeated addition, how many operations would you have to perform? How many additions would you have to perform? Any guesses? Right, but X is a 20-digit number. So how big? So how many times do you have to keep adding it to itself? Yeah. 10 to the 20. Okay. So if I use repeated addition, I would have to perform 10 to the 20 additions. To get a sense of 10 to the 20, my CPU, performs about 10 to the 10 ops per second. And let's say you can even add two numbers in a single operation. So that means it would take about 10 to the 10 seconds. Okay. Any idea how long 10 to the 10 seconds is?
Years.
300 years. Okay. So to add two 20-digit numbers using repeated addition on on my MacBook M1 Pro would take 300 years. Okay. But let's say, I go to a fifth grader now. So if they were using the algorithm that which is grade school multiplication, what happens? How many operations can probably, okay, so how fast can a fifth grader add numbers? Maybe let's say 10 seconds per operation. Okay, I think it's pessimistic here. Right? And if I had to add or multiply two 20-digit numbers, how many operations does the grade school algorithm take? Any guesses? Yeah. 400, right? Because if you go to the loop here, you have like I equals 0 to n minus 1, j equals to n minus 1. And for every value of I and j, you have one operation, right? So that's going to be 400 operations. So this is about 4,000 seconds. Okay, and how much is 4,000 seconds? Maybe about 70 minutes. Okay, so a modern computer with a bad algorithm is so much worse than a primitive computer like a fifth grader with a good algorithm, right? So the algorithm makes a huge difference here. Kind of the most significant bit. It's like, there's not even a comparison, 70 minutes versus 300 years. Okay, so the algorithm that we use can have a dramatic effect. Okay, just as how we represent the data can have dramatic effect. Okay. So just as a kind of anecdote, let me say a little bit more about multiplication. So grade school multiplication, as we saw, takes, if I had to multiply two n-digit numbers instead of two 20-digit numbers, takes about n squared operations. Okay, because we have two for loops, each one going from 0 to n minus 1. So you end up with roughly n squared operations. Okay. And the question is this the best possible? So is n squared the best possible? And so there was a very well-known mathematician, Kolmogorov. You might have heard his name. In the 1960s, he asked this question, is this the best possible? And he started running a seminar at his institute where he wanted the undergrad students to prove that this is the best possible. And there was one student, an undergrad, who, Anatoly Karatsuba, so what did he do? He said that actually this is not the best possible. There is a better way to multiply numbers than to do grade school multiplication. It's not the best. You can do it with n to the 1.6 operations. Okay, so you improved it from n squared to n to the 1.6. And after so many years, we believe we have the best one. Currently we can multiply two n-digit numbers in some constant times n times log n operations. Okay, so even a simple problem like multiplication, is like took a long time for us to really at least nail down or what we believe is the right time complexity. How many operations do you need to multiply two n-digit numbers? Okay, and so what we are going to do next is to ask. No, unfortunately not. It's a huge open problem. We know it has to be at least n, some constant times n, because you have to read the two things, but we do not have any notion, any way to show that n log n is best. Okay, but today, in this course, before we get to n log n versus n squared and so on, that I would say is kind of very important. But first, we need to know that we can compute this. At least for multiplication, we already had an answer with one algorithm. For many other problems, we don't even have the starting point. And we're going to ask, is there a good starting point or not? Okay, so what can we actually compute? If I ask you something and ask you to show that, okay, you can solve this problem on a computer, it's, I would say, relatively easy because you can give me an algorithm. Right? I tell you, okay, tell me how you can multiply two n-digit numbers. You will give me an algorithm and show that, okay, it is done, right? But what if I ask you, what can't you compute? Now, this is a much trickier question to answer, right? You have to show that there is no algorithm whatsoever for this problem, which is, it seems much more difficult to rule out. Okay. So what we're building towards is a way to answer, well, let's say, okay. So we have to first, well, okay, so let me say it this way. So for these two questions, what can we actually compute? What can't you compute? This is kind of like asking, can a computer solve a problem P? Again, I'm being deliberately vague here. We'll become more specific and much more mathematical soon. Suppose my problem is, okay, I give you a graph, tell me if two vertices are connected. Okay. Another problem might be like a jigsaw puzzle. I'll give you a bunch of puzzle pieces. Tell me if they can fit together in some nice square. Okay. I give you a program. Tell me if there is a compilation error in this program. If I run it through a C compiler. So I give you a C language text, some text which I'm saying is a C program. Can you tell me, does this have an infinite loop within it? Right? All of these are specific computational problems, and we'd like to know if you can answer them or not. So if I ask you this question, there are kind of two things. First, we need to come to an understanding or formalism, which captures exactly what it means to solve a problem, right? And this has to be done rigorously. What it means. Okay. So this is relatively easy. We can specify mathematically what we want from this computation or from this algorithm. But then we have to also specify, define what an algorithm is. Okay. And one of the most important things that we'll build towards is a very simple, almost toy-like model that captures all forms of computation. All forms, by all forms, I mean really all forms. It's like, you might say, okay, tomorrow I might have a quantum computer, maybe that will solve the problem. No, this toy model is just as good. Okay. You might think of any other crazy like distributed systems, whatever, this is just as good. And interestingly, this was done back in 1936. Okay, this model. It was introduced by Turing. It's a really Alan Turing in 1936. It's a really ingenious model, very simple in hindsight for what it's achieving. Okay, and in terms of impact, I think Turing's theory is really, in my mind, at least, far greater than Einstein. Okay, as we'll see, this model of computation is very universal, and we'll exploit it in answering some very important questions. Okay, so let's take a 5-minute break, and when we come back, we'll start talking about representations in a bit more detail. All right. Okay, sorry about that. I'll make sure I won't forget starting recording next time. Okay, so we have all these different kinds of objects that we see and manipulate and operate on our computers. But if you go to the hard disk, at the end of the day, it's just a sequence of zeros and ones. Okay, there's some program which is sitting on top of the hard disk and then kind of really allowing us to see this folder structure, each file and so on, right? But the hard disk itself is just one sequence of zeros and ones. And if I give that sequence to any other computer with the same program, you get the same sort of output. And we often take this representation for granted. And for good reason. Like, if I ask you to design an algorithm which kind of translates one text into the other, you don't start with, okay, I have 0-1 sequence, I interpret it as an English text, and now I have to translate into Spanish maybe, and something like that, right? That's too low level for us to keep doing it again and again and again. Okay. So for instance, like if I say, when you design an algorithm, you'll say program P, maybe it takes image X as input, or takes, numbers, X comma Y as input. maybe takes list L as input and so on, right? We don't start thinking about the sequence of zeros and ones every time, right? But as I said, our goal is to really make sure that everything is on a strong foundation. How can we assume, how are we bridging this gap? How can we assume that we are operating on this higher level objects while our hardware only supports sequence of zeros and ones? Okay. So what we'll do is we will open up this box once. Okay, so for once, let's open up this somewhat of an ugly box and see, I wouldn't say ugly, but somewhat of a complicated box, and see how are these things being represented as zeros and ones. We'll do it once, and after that, from then on, everything, any data object for us will just be a sequence of zeros and ones. You kind of give us a simple and realistic way to talk about what our computers or what our models of computation are getting as inputs. It'll just be sequences of zeros and ones, because we know that every image, every video file, anything like that is at the end of the day just a sequence. Okay. And the main idea here, the big idea, the punchline is that we can compose okay. So what do I mean? So there is an abstract way to go to do the following. If you can represent objects of type T, let's say I tell you, you can represent integers as sequences of zeros and ones. I tell you there's a way to represent images as sequence of zeros and ones. A text file, a sequence of, just words as zeros and ones. We can automatically find a way to represent lists or, collections like tuples of objects of type T. Okay, so there's a compiler which can do this, which takes one kind of way to represent objects of type T and gives you one level higher up. It gives you a way to represent lists of objects of this type, again as a sequence of zeros and ones. When we see it in action in some, we'll have a demo next lecture, and then it'll be, I think it's pretty striking. And at the end, this allows us to denote all objects as sequences of zeros and ones. And this way of composing is actually at the heart of object-oriented programming. You can build objects on top of objects and so on using kind of similar tricks. Okay. But before we go there, let's talk about what we mean by representations, right? What do I mean by representation? So let's try and start with the even more basic question. How do you define representations? Okay. So before doing that, let me introduce some notation that you might be familiar with from discrete math. So if I have a set A, maybe it's just a collection of zeros and ones or numbers and so on. I might have another set which is A squared, okay, which is kind of shorthand for A times A, right? Which is collection of pairs of objects from type A, right? So this is all things of the form A comma B, where the first element is in the set and B, the second element is also in the set, okay? And I also have A cubed, which is A times A times A, and A, B, C. And so on and so forth, like an A to the fourth, A to the fifth. And there's something called A star, or this is called the clean star operation. Okay, this is just a fancy name for A union, A squared union, A cubed union, so on. Okay, and you also, just for convenience, include the empty symbol. Okay, so this is just to write the empty word. Okay, so what does this mean? A star denotes all finite sequences where each element is from the set A. Okay, it's just some notation that's very helpful as a shorthand. So for instance, if I take A to be the set 0, 1, then what is A star? You know, what will be A star here? It's just all possible sequences of zeros and ones, right? You'll have, you know, the empty word and 0, 1, union 0, 0, 0, 1, 1, 0, 1, 1, and so on and so forth. Okay, all possible sequence of zeros and ones. All right. And what we are looking for is a way to represent objects as just elements of 0, 1, sequence of 0, 1s, right? So imagine, so to define representations, we want, you know, I have some collection of objects, be it images, numbers, you know, maybe words, you know, sequence of strings, whatever. I want a representation of those things as 0, 1 star things. Okay. So when I say it's a representation, what would be the most important property for this function E to have? Any suggestions? Yeah. Yeah, you should be able to define inverse of the function, but you know, it's equivalent to what you're saying, but let me say it is 1 to 1. Okay, and we'll call it the encoding function. All right, so you gave me an image, I'm encoding it as a sequence of zeros and ones. You gave me a string, I'm encoding it as a sequence of zeros and ones. And the most important property, and the only property that we really care about for this encoding right now, is that it be 1 to 1. I don't want two images which are different going to the same binary string, because then it's not a good encoding. I want the encoding to be a representation, meaning when I give you the representation, I can somehow go back to the image, right? Okay, yeah.
Data here is just some arbitrary input.
Some arbitrary set, you know, it could be images, strings, you know, maybe graphs, whatever. Okay. Any questions about this? So, yeah. No, not necessarily at all. Okay, so we really only care about the forward mapping here, which is going from the object to a sequence of zeros and ones. It's a good question. Any other questions? All right. And one thing, you know, again, you might have seen or might be contrary to what you might have heard before, but in this course, at least, definitions are the most important part. Okay, so understanding the definitions, as I said, our goal is to define what computation is, right? So throughout this course, understanding the definitions should be the most important thing, kind of the foundation that things build on. And then theorem statements. We'll state various properties and conclusions, and they are more important than the proofs. Okay, so try to understand the definition first, which is as I said, very critical. Once you understand those, try to understand what the statements that we're going to make are. Okay, after that, the proofs. Right, so the main takeaway should be the definitions, the statements, and maybe the proofs as well. Okay, so we understand what we are defining representations as. These are encoding functions. It's just any mapping to the set of all possible binary sequences, and has to be one-to-one. That's all. Okay, so let's do some examples just to kind of get our get a sense of what's happening here. So example 1. So let's try and represent natural numbers. Right, so I want an encoding function E from the set of natural numbers to binary sequences. Okay, and just as a convention, the text follows this and we will use it too. So natural numbers for us will include 0. Okay, so we're always going to use indexing which starts from 0 and so on. So let's just make this convention that natural numbers includes the number 0 as well. Okay, so what's one way to encode natural numbers? Any suggestions? Binary. Okay, so there's something simpler though. Let's just do the simpler one first, which is unary. Okay, so unary is just you denote a number n as a sequence of zeros, let's say n plus 1 zeros. So E of the number 0 would just be the sequence 0. E of 1 would be 0, 0. E of 2 would be 0, 0, 0, and so on. Okay, and that is one encoding. That is one way to represent natural numbers as a binary sequence. So from now on, if you wanted to, you could just assume that a number, whenever you're doing operations on a number, it's being denoted in this unary format. It's definitely not the most efficient. It's very cumbersome. Okay. Another thing, another representation, the one that you are hopefully familiar with is binary encoding, right? So here E of 0 would just be 0. E of 1 would be 1. E of 2 would be 1, 0, and so on, right? Okay, but let me define it just kind of formally so that we have this mapping. So I'm going to call it natural numbers to binary, n to b from the set of natural numbers to 0, 1 star or 0, 1 sequences, and it's defined as follows. Of course, there are many, many different ways, but I'll just write down one way. Many different ways to write it down succinctly, all of them giving you kind of the more or less the same representation. I'll say it's 0 if n equals 0, is 1 if n equals 1. Otherwise, it's you compute the binary encoding of n divided by 2, the floor operation. Meaning you're rounding down. If I have 5 5 by 2 is 2. Okay, if I have 6, 6 by 2 is 3. And just concatenate it with whether n is odd or even. Okay, so this is one way to compute the binary encoding. It's kind of a recursive way. I just divide by 2, compute that, the encoding for that, and then tag on a 0 or 1 at the end, depending on whether the number is odd or even. Okay. Any questions about this? All right, so I'm saying this is an encoding, but to really know that it's an encoding, we have to check whether or not this mapping we defined, this function, this encoding function is 1-to-1. Okay. How can I show that? Use a proper encoding function. Okay. Any suggestions how you might prove such a thing? Yeah. I'm sorry, say it again. Yeah, you could use induction or just kind of looking ahead. Let me suggest a different way, which is there is the encoding function is 1-to-1 only if there is a proper decoding function. What do I mean? E is a valid encoding function if and only if there exists a decoding function. Right? Meaning a function D from 0, 1 star to the set of objects that you're working with, such that if we apply the decoder on the encoding of an input, what should the answer be? You should get back the same thing that you started with, right? I went from the object to the sequence of zeros and ones, but now if I use the decoder function, I should get back the original object. Otherwise, we lost some information, which we shouldn't. We want this representation to be without any loss in the information, right? Okay. So for instance, for n to binary, you can easily define a decoder, which is, you look at the position of the thing, position of each bit, and then multiply it with the corresponding power of 2. Okay, that's how you can go from like binary representation to the usual representation. So that's a valid decoding function, and hence is an encoding function. Okay, you could also use induction to prove it, but the decoding way of looking at it is useful as we go ahead. Okay, any questions about this? All right. So let's do another example, which is maybe a bit, slightly more complicated. How can I represent the set of integers which have, even the negative numbers as zeros and ones? Any suggestions? There are many, many different ways. Just come up with one. Yeah. Yeah. So I can define a new encoding function which takes an integer and does the following. So the first bit, what I write down at the first position of the encoding is always going to tell me whether or not it's a positive number or a negative number. And then I can use my, let's say, n2 binary. Okay, so we're already composing representations. So we are using our ability to encode natural numbers to design an encoding for integers.
Something that hyperblue float is not a valid encoding? Not-
Well, float is kind of limited, right? You have a precision there. So it's different. It's only meant for numbers up to certain range. Whereas here we're working with any possible thing. But even when you have libraries which can represent any big number by composing these things. Okay. So for instance, so to define this formally, this would be 0 and then concatenated with n2 binary of n. Let's say if n is greater than or equal to 0, 1 and n2 binary of minus n if n is less than 0. Okay, this is just one convention. Yeah.
How do we ensure the concatenation operation notate with this notation?
You know, and sometimes I'll just write the concatenated like the little circle. Okay. Or sometimes I'll just write down when it's kind of not too confusing, I'll just write it down next to one another. Okay. And as a warning, and maybe this is connected to the question that you're asking, this is not the one actually used. This is not the representation that we use on our computers. We use something called two's complement representation for very different and good reasons. But this is one valid encoding of integers, right? And there are many, many different encodings. We're just picking one. Yeah. Sorry, say that again.
Your microphone's on.
Oh, it went dead. Sorry about that. Maybe I should get my own batteries next time. Okay, I'll try and shout for the remainder of this lecture. Might be unpleasant for the Zoom people. Reduce your volumes. Okay. So there are many different ways to represent integers, but we saw one way to represent integers here. Okay. Let's take a step further and see another example. It might seem a bit tedious, but all of this has a plan. At some point, we'll hit a principle which will allow us to represent arbitrary things. We're trying to identify it and kind of get there in a sequence of baby steps. We saw one way to compose things already. We use the representation power of integers, of natural numbers to do integers. So what would you like to do next? Yeah, maybe. So let's do rational numbers. Is that what you said? Images. Okay, that's way ahead. I thought you said fractions, but you hear what you want to hear. Right? So rational numbers. Okay. So things like 1/2, maybe 2/3, even negative numbers, negative rational numbers. How can I represent these things as a sequence of zeros and ones? Any suggestions? Yeah. Okay, so that's an excellent suggestion. So we can first of all think of this as a numerator and the denominator, right? This is like 2, 3, the numerator and the denominator, the numerator and the denominator. But how do we go to just a sequence of zeros and ones? Any suggestions? Yeah. So, that's again, we want to do it from first principles, right? So just using what we already saw, if you had to only use that, how would you go to represent the numerator comma denominator pair? And you can already see we are going from being able to represent one object to a tuple of those objects. And we're trying to identify that. So this is two numbers, right? A numerator is a number, denominator is a number. You can even think of positive rational numbers. So you just have two natural numbers. Yeah.
Really just using raw zeros, use a block that's separator and stays inside it.
Okay, so maybe let me take a babier step first and then come to your suggestion, which is maybe I'll just do an encoding of, so let's call this, let's say this is P and this is Q. And I'll try to do Z2 binary of P and then just do Z2 binary of Q. Okay, I compute then encoding of the number P, encoding of the number Q. And is this a good encoding? No, right? Because we don't know when the numerator starts and when the numerator ends and when the denominator starts. So if I just use this is not a valid encoding. So for example, if I do something like, let's say, 1, 3 would be mapped to 1, 1, 1. Okay, which is the same thing as 3, 1. Okay, so two different rational numbers are going to the same string. So this is not a good encoding. And the problem is we don't know when the numerator is ending and when the denominator's encoding is starting in our sequence. So we need something kind of to tell us there's a break here. But we can't put like a comma because we only have zeros and ones. We don't have any other symbols. So what would you do? Any suggestions? Yeah. Yeah, that's a good way. Or maybe let me slightly modify your suggestion and say, maybe I'll do the same thing here, which is I'll do the concatenation, but I will write down how many bits correspond to the numerator. Okay, using unary. It's kind of slightly more efficient than what was suggested, right? So suggestion, maybe I'll write down what you suggested as well, because it's definitely valid encoding. The first suggestion was use the unary representation. Unary representation of P, we know this only involves zeros. Put a 1 and then unary representation of Q. Okay, now we know exactly where 1 is ending and 1 is starting, so we do get a good way to separate things. Another suggestion, which kind of motivated by the same thing, is first put a sequence of zeros, which tells you the number of places corresponding to the numerator. Okay, followed by a 1, and then whatever we had before. Okay. So we're just addressing this issue that we didn't know when the numerator ended by kind of appending that explicitly at the beginning. All right. Any questions about this? Any other suggestions? There are many, many different ways. Any other suggestions for how to do this? Yeah. If you interleave them, that almost works. But what if there are different lengths? Yeah. So suggestion number 3, in fact, if you pad them, then you don't even need to interleave. So Z2B of P Z to B of Q, paired with zeros to match lengths. Okay, you're going to put zeros at the beginning of these numbers because then it doesn't change what number you're representing, but the lengths match. So half of it will always be the numerator, half of it will always be the denominator. That's another encode. Okay. So there are many, many different ways of coming up with this encoding, but we're going to look at one way to do it for the one reason that it extends very nicely to many other encodings. It's not kind of specific to just numbers and rational numbers, kind of allows you to compose things in an easier way. And it's also something very easy to code up in Python, as we'll see. So suggestion 4, I'm going to say is the following. And to define this, let me introduce a new encoding, which I'll call Z2 binary with a bar to separate it from the other encoding that we had. Okay. So what I'm going to do here is take your old encoding and duplicate each bit. Meaning, take your old encoding, replace each 0 with a 0, 0, replace each 1 with 1, 1. Okay, you do this for every bit in your encoding of Z to B, and then you end with 0, 1. Okay. Essentially, what I'm doing here is kind of putting a special symbol which allows you to understand when this encoding has ended. Right? So to be clearer, so now the representation for something like 3, maybe let's do 2, would be so Z to B of 2 would have been 0 to denote it's a positive number, and then the binary representation, which is 1 and 0. Okay. So what would Z2, the new encoding, be? It's 0, 0, 1, 1, 0, 0, because I'm kind of duplicating each one. And then I end with 0, 1. Okay. That's my new representation. All right. And once I have this, I can now define a new encoding. The new encoding of natural numbers to 0, 1 star. Let's call it Q to S of P over Q is just Z to S bar of P concatenated. Sorry, it should be binary. Okay. So I can concatenate with this new thing because the 0, 1 will tell me when the numerator has ended. I keep going from left to right. Once I say 0, 1, I know the numerator has ended, and I'm starting the denominator. Yeah.
They'd be more efficient when only use CPP bars rather than the visual of the code.
Yeah, definitely. That's also possible. It'll give us a more efficient way. And but let's first talk about this, and then I'll address your point. That's an excellent question. Okay. So what's happening here, right? So the claim is, let's say, proof Q to S is a valid encoding. So we want to say that or let's say claim Q to S is a valid encoding. Again, the proof is fairly straightforward because, as I said, one way to prove something is a good encoding is to come up with a decoding algorithm. You just describe how you would go from your binary sequence back to your P comma Q, and you would be done. So let's write down a decoder. Right? So let's call it S to Q, so that S to Q of Q, B to Q, so that B to Q of Q to B of a number gives you back the number, right? So that's our way to certify something is a valid encoding, right? One way to certify. And this is simple, what we discussed. Keep reading until you see 0, 1. And before this is numerator. After is denominator. Okay, simple, idea, right? So if you kind of work it out, for example, Q to be a 1 over 2 would be and you get something, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 1. It feels like, we increase the length a lot, but this is a valid encoding. This binary sequence corresponds to 1 over 2 and nothing else. Okay. And so let me ask you a question. Why should I have to duplicate each bit? And why can't I kind of, maybe just add 0, 1 at the end and use that as an identifier? Yeah. Exactly. You might have 0, 1 inside. If you have the number 5, it's 1, 0, 1. So you don't know where it starts. That's why we're duplicating. We're kind of creating a special symbol essentially by making sure that our encoding does not have the sequence 0, 1. Okay. And the abstraction here is that we can use this as a template. What we really did here was we started with a representation of integers and went from there to a representation of pairs of integers. Okay. So this is our kind of, hammer that we're going to use. If you give me a way to encode something, I can use this trick to get a way to encode pairs of those objects. Like, if you give me a way to represent images, now I can represent 2 images. Okay. And then we'll extend it to multiple images and so on. Right. And when we come to next lecture, that's what we're going to do. How can I extend this from 2 to 3 to 4 to 5 and to not just integers, but arbitrary objects? All right. And I'll say a few things about the efficiency of this representation too, as pointed out earlier. Yeah. Yeah. The negative fraction, you mean like -1, 2? Right. So let's adopt the convention that will push the, the negative number. The numerator is negative and the denominator is always positive. The numerator is negative or positive. The denominator is always positive. Okay. Yeah. So this is 1. This is 0, 0, and this is 2. So it really depends on the class size. Definitely no PTs because hold on one second.